Okay, hello everyone. Welcome back to my YouTube channel, and welcome back to my series of videos related with HVDC systems. Okay, we have been recording few videos related with DC transmission systems, and this is one of the videos related with numerical examples of using DC transmission systems. Okay, I am sorry that I need to use my handwriting and also fixing some typos, but I had a very hard time with Microsoft this week, and as a consequence, there are some issues related with the transcription of my classes. Okay. Also, some documents disappear. Okay. Thank you very much for watching my videos, and let's start here. We have the problem. I think this is 1.8. And 1.8 is related with operating conditions in voltage source converters working inside HVDC links. Okay, again, a problem. Okay, 1.8, and we are working with operating condition of a voltage source HVDC link. Okay, you can imagine that in this case, the voltage source converter is connected to a 33 kV AC system. Okay, we are using a 33 kilovolts AC system. This is a line-to-line voltage RMS that is applied to the voltage source converter, and this supply is coming from a system that the short circuit level is 150 AVA, okay, MVA. Any one of you that is still confused about the understanding of short circuit levels, please go to my classes of short circuit analysis. Over there we discuss how to obtain those numbers and how to use those numbers. Okay, for all my students taking my classes and attending regularly to the classes, they must be familiar with this. Okay. And this voltage source converter is sensible in terms of voltage, and the voltage, this voltage source converter operate with a voltage between 0.7 and 1.2 per unit, okay? We must be careful, voltage source converter, quite sensible in terms of voltage, okay? And also this voltage source converter have a reactance that is coupling. This coupling reactor is 21.8 ohms. Okay. If we assume that voltage, and again there is a thing here, voltage at the AC system is 1 per unit, and we assume that as a very big bus bar of 150 MVA, and using a base of 150, calculate, okay? First, what is the maximum active power that this DC link can export to the AC system? Okay, that is the first question. Second question, what is the angle that is inside this voltage source converter when we are operating at 10 megawatts exporting power? Okay. Then, what is the maximum reactive power that the DC link can inject into the AC system? And then, what is the maximum reactive power that the DC link can take from the system? Okay. Be careful with questions C and D. One is what is the maximum reactive power, but injecting into the AC system. Sorry. And the question D is related with absorbing from the DC system, okay? Okay, as usual, I highly suggest to my students, the first step must be creating a graphical representation of the problem, okay? What is the graphical representation over here of this problem? Well, as you can see, we have here the DC link. This is the DC link. We have the voltage source converter. We have a line that is connecting to the system. And the system have a reactance that is coming from this short circuit level. And all my students must remember that the reactance of that system is equal to 1 per unit based on this 150 AVA, okay? I will not discuss here, but all my students know that. If not, go to my short circuit analysis classes, okay? This is the bus bar for the 33 kV connection, okay? They are 33 kilovolts over there. This is the equivalent internal voltage of this converter. And here we have the line, the 21.8 ohms, okay? Okay, good. What is the first steps here? Well, the first step, I already put here one answer. The first step is calculating the per unit values, all of them at the same base. Strategically, we are using 150 MVA as a base in order that this one is 1 per unit. But for the line, the value is 21.8 ohms. That is the data for the coupling reactor. And we need to use the impedance base, okay? If we put the number together, we use voltage base as 33 kilovolts dividing by 150 AVA, we can get an impedance base of 7.26 amps, okay? 7.26 ohms, sorry, okay? Then we refer the coupling reactor. The coupling reactor is referred to the per unit system, and we obtain here 3 per unit. That is the representation, that is the per unit value for the beautiful coupling reactor, okay? Next step. Okay, next step is very simple, okay? Very simple, because next step, let me keep this like this, okay? Because the maximum power that we can send from the voltage source converter, okay? You must remember that we have an equation that defines what is the power that we can send from the voltage source converter up to the external system, okay? And you must remember that the power that is moving across those reactants depend on the product of the voltages and divide by the total reactance, okay? Here we have a series reactance, and because we have two reactants in series, the total reactance is the sum, okay? Something simple for my students. And what we need to do is, okay, I need to calculate the maximum power that depends on the product between the voltages and divide by the total reactance. Total reactance 3 per unit plus 1 per unit, that is 4. And the numerator, you can see this voltage and that voltage. As you must remember, we have a voltage at the system and we have a voltage at the converter, okay? In this case, if we assume the maximum voltage coming from the converter, 1.2, and we assume, or we know because it was a data, that the AC system is working at 1 per unit, well, the maximum power that we can get here is 3 per unit, okay? Be careful here, okay? Because here we are using the maximum voltage, we are using the maximum VSC maximum, and that is 1.2 per unit, okay? Why not using 0.7? Oh, wow, come on, guys. If you use 0.7, you will get a less power, less active power, and that is not the idea. The idea is that we want to know what is the maximum active power that we can take out from this converter, and that situation is basically when we are using 1.2 per unit as a setting of the internal voltage of the voltage source converter, okay? Good. Now let's move to the next question, okay? Well, 0.3 per unit, but I want this number in real values. And as you must be aware, 0.3 per unit, you multiply by the base, that is 150 megawatts, and multiplying 0.3 by 150 megawatts, we obtain 45 megawatts. That is the maximum active power that we can deliver, but we can deliver this only if we have internal voltage of 1.2 per unit, okay? This is a very nice question. It's something that put my student to think about how the system behaves, how the system works, okay? Okay, let's keep moving. Now the next question is, okay, what's happening if we are using this converter and we want to deliver 10 megawatts, okay? Well, if we want to deliver 10 megawatts, what we need to do now is using the same equation, but now we are using a value that is different to the maximum. And for that reason, I would like to know this angle delta that allow me to deliver 10 megawatts, okay? In this side, I will use per unit values, 10 megawatts divided by the base. This is the base, okay? We obtain that the angle can be obtained by removing from there delta, and as you can see over there, we obtain 12.83 degrees, okay? That is the angle that you need inside the converter in order to deliver 10 megawatts when the internal voltage is 1.2 per unit, okay? Good. Now let's move to the next questions. Now there are a few interesting questions coming up, okay? Now there is a question, what is the maximum reactive power that you can inject into the AC system, okay? And all of you must know from the theory, and we explained that in we explained that the maximum reactive power is happening when the phase angle between the internal voltage and the system voltage is 0 degree, okay? That is the moment that we have pure reactive current, okay? I don't know if you realize, but this equation over here is coming basically from voltage divided by reactance, okay? But if this angle is 0 and this angle is 0, that means that the voltage difference over here will be 0 degree. And divided by the total reactance, this current will be a capacitive current. This current will be reactive current, okay? And what I'm trying to tell you again is that the maximum reactive power production happens when the voltage source converter has the voltage in phase, okay? And because we want the maximum reactive power production, we are using again 1.2 per unit as the internal voltage of this converter. That is a key point here, okay? Well, then, what I want to know is we have the output of the converter at the very end of the coupling reactor. And we call that point the 33 point, okay, voltage 33. That is the terminal of the converter that is immediately after the reactor, okay? I will try to show you here. Sorry about what I am telling you is this reactor over here, this is the coupling reactor. And when we are talking about injection of P and Q, we are talking about the power that is delivered from that point onwards, okay? And it's extremely simple to calculate the voltage in this point, okay? The voltage in this point can be calculated basically using Kirchhoff voltage law. We use over there Kirchhoff voltage law, and as you must be aware, we are calculating the voltage at the 33 kV location, and we obtain that voltage is, remember, this is 1.2, this is 1.0, and this voltage is calculated and is 1.05, okay? All of them are 0 degree, 0 degree, and 0 degree, okay? And let's see, I think there is a issue over there with the, yes, that is a issue, because this voltage should be equal to this voltage plus this voltage, okay? Okay, yes, it was a problem here with this positive number over here, this positive sign over here, and J multiplied by J is -1 multiplied by this minus, that is a total of positive. That means 1.0 plus 0.05, that is 1.05 0 degree, okay? Again, what is happening here is this is positive, okay? And what is happening is J multiplied by J is equal -1, but we have here is minus J multiplied by J, that is a +1, okay? That is the situation over there. Okay, but now what I want to do is, how much is the reactive power here, the output of this converter? Well, it's extremely simple. What we need to do is calculate the imaginary part of the converter. This is the complex power at the 33 point, or the output of the converter, and that is the voltage multiplied by the conjugate of the current, okay? And what I am putting here is basically the voltage that we calculate before, this voltage over here, multiplied by the current, but the current must be conjugate. This symbol is positive because this conjugate, and when we solve this product, we obtain that there are 0 real component and only imaginary component, okay? Okay, this is Qmax. Okay, now taking the imaginary component, that is the reactive power output, okay? And now multiplying by the base, and you must remember that we are using 150 MVA as a base, we obtain that the maximum reactive power is 7.875 MVR, okay? As you can see, this converter is able to deliver a maximum active power of 45 megawatts. Okay, you must remember that the maximum power, active power, that this converter is able to deliver is 45 megawatts. And now from our calculations, the maximum reactive power that this converter is able to deliver to the system is 7.875, okay? Now, what we want to do is calculate the maximum reactive power absorption, okay? And in this case, that is happening when we are using the lower inner voltage inside the converter, okay? What we need to do is something similar at what we did before. We are using again the calculating the current. What is the total current? And here we have again another typo. Let me finish this here. Yes. Okay. And I know that many of my students, if they don't have the full explained solution, they will come back and email me. And to avoid that kind of email, what I will do here is, okay, we are using 0.70 degree minus 1 at 0 degree divided by 4j, okay, and this is equivalent to minus 0.3 divided by 4j, and from there, okay, you obtain this value, okay. You must understand that this j, when they move to the top, is a minus j multiplied by minus. That is the reason for the positive sign over there, okay. Then, okay, we need to fix this equation because this equation is positive, and then what we will do is, remember, this equation is positive because we have here the power converter. Yes, we have here the power converter. We have the reactor, the coupling reactor. We have the system over here. We have B33, and we have here the AC voltage. Okay, and those voltages, if you remember, the current is going in this way, and the equation that is defining this is this voltage is equal to this voltage drop, and that is plus this voltage AC, okay? I am including all of this because I don't want to receive more emails asking about detailed equation, okay? I prefer to use my ugly handwriting and solve the problem here, okay? If you put the number together as we are expecting, right now we have here 0.7, we have here 1 per unit, and right now, because we are the reactive power is absorbing this device is absorbing reactive power. This voltage is 0.95. Okay, that is the condition of this system, okay? And now what we are doing right now is calculating the total maximum reactive power. And in this case, as you can see over here, multiplying by the base, we can obtain that in this case, this converter is able to deliver to absorb a power that is 10.4 MVar. Okay, what is the conclusion over here? The conclusion is that this beautiful converter that we have been using, this beautiful converter that we have over here, okay, we have here the DC side and we have here the three-phase. Okay, this is the three-phase and this is the coupling reactor. Okay, this gentleman over here is able to deliver a maximum power of 45 megawatts, and at the same time this gentleman is able to deliver a maximum injection, okay, of reactive power. This is a maximum injection of 7.875. Okay, when this is 1.2 per unit, and then they can absorb 10.4 MVR when is 0.7. Okay, in this case, this is injection, and in this case, it's absorbing. Okay. Okay, well, I think this is a very interesting and very useful example. I am sorry about my ugly handwriting, and also I am sorry for my all the typos here with this Microsoft Word issue that I have, and I'm sorry about that. However, I believe this is the best example that you can get for voltage source converter, numerical equations, and also to use in your mind to understand how a converter behaves injecting reactive power, absorbing reactive power, how the variable must change in order to deliver more reactive power or to deliver or to absorb reactive power, okay? I believe all my students now must understand that those voltages, the internal voltage of the converter is a relevant, a very important variable defining the behavior of this converter in terms regarding reactive power, okay? Well, I think this is the last example, and thank you very much for watching my videos, and thank you for subscribing to my YouTube channel, and thank you for the emails that we are receiving. I appreciate your help and your support, and feel free to follow me on Twitter or LinkedIn, and more than happy to give you some help if you need it, okay? Thank you very much for watching my video. See you in a future video. Thanks very much. Bye now.